Charlie, are you ready?
Yep.
Okay. So good morning and to American colleagues, and good afternoon again to our European colleagues, and good evening to our Asian colleagues. Welcome again to this World River and Delta Source to Sink webinar series. Today is the Source to Sink 2021-05, number 5. So we invite Professor Charlie Paull from Monterey Bay Aquarium Research Institute come here, give a talk about the tracking the movement of the sand through Monterey Canyon. So we appreciate this effort for Charlie because now is 6 a.m. In California. So thank you, Charlie, very much. Before I introduce Charlie, as always, I want to mention to you about our past talk in last year. Now we have 40 talks archived very well on the YouTube channel. So including the first one, Chuck Neutral will talk about the Amazon. So the website is just very easy on the YouTube channel, tinyurl.com/S2S talks. And also for the Chinese colleague, if you cannot access directly the YouTube channel, you can go to the B station. You know, this is the backup copy of all presentations. So Charlie, here it is. He had a very, very rich experience. I want to say is briefly graduate from Harvard College and then go to University of Miami, marine geology and geophysics. I think this is after my mentor, John Miniman, left there, right? So you have a little bit late behind him. So then he got a PhD from Scripps and so in 1986. And also, as you can see, also a visiting scientist at ETH Zurich, and also spent some years in North Carolina. It's just our neighbor, you know, UNC Chapel Hill, and then moved back to Western Coast. And as a senior scientist is Monterey Bay Aquarium. And Charlie is very famous about his study in Monterey Canyon, turbidity current, and the geohazard, gas hydra. And so particularly focus on the observation of the submarine canyon dynamics, you know, the real field observation. So one thing I want to point out, Charlie received Francis Shepard Medal in 2019. So I think he's very well deserved this. A bunch of the medal receiver actually already also in the speaker of this talk series. So we are very honored to get him today give us a talk. So Charlie, I will stop sharing. Please go ahead, share your screen and put a presentation mode. Okay.
So thank you, Paul. Is this the right screen?
Yes.
Great. So I'm going to be trying to track the movement of sand through Monterey Canyon. And before I start, what I'm going to present today is the product of many people's efforts. I'm really looking at Monterey Canyon, which starts at the shoreline in Monterey Bay, and of course it extends for more than 400 kilometers off shore. Now, in this talk, I'm going to go down through a series of available data that allow us to think about this as a system. And it's going to start with just looking at the coastal sand budgets. I'm going to move on to mapping the canyon floor, then to monitoring efforts to try to capture the movements as they go on, to sampling efforts, repeat mapping, and then repeat coring activities. And just to start off with, the canyon head for Monterey is really right at the shoreline. So it is in a position to capture the sand that's moving along in the longshore transport system. Now, there is no significant river system at the canyon head, but the Salinas River, the Pajaro River are offset by a few kilometers. There's also sources of sand from eroding seashore. Now, this has been a topic of study for a while in terms of what the coastal sediment budget is, and there are multiple studies of this. They, like any place, collect a scattering of numbers for their estimates that are shown here. But if you put this all together and given the vagaries of they're made with slightly different techniques at different time intervals, et cetera, there's something like 500,000 cubic meters of sand that is going down Monterey Canyon or disappears into the canyon every year to balance these sediment budgets. I'm just going to take that number as a sort of a consensus number the times I use it in this talk. I'd also like to point out that MBARI is positioned directly at the canyon head. So my institution has focused some efforts at trying to develop technology to study the canyon. And what we're going to do in this talk in a way is to account for the sand that goes down the canyon over the last approximately 20 years. Now, moving on to mapping of the canyon, I'd like to point out that it's, again, starts at the shoreline, goes out to more than 400 kilometers, and there is a sort of continuous fall wag that runs out offshore. That's what I have highlighted here in red and in many subsequent slides. Now, we know this because Monterey Canyon was mapped in 1998 with a EM 300 system, with a 30 kilohertz system, which was the state of the art at the time. It's now no longer quite as current, but it's not far different than the best multi-beam you can get from many of the UNOLS vessels still. And I'd point out that another aspect of the canyon is that there is a break in slope that happens at about 1,300 meters along this thalweg, where there's a granodiorite sediment mass that forms a sill in the canyon. It's called the Navy slump. Now, continuing the theme of mapping, the surface ship multi-beam data that was collected did not reveal that there were any bed forms in the canyon floor, but that the presence of significant bed forms was discovered by the Cal State Monterey Bay group starting in 2005, when they used a multi-beam launch, again, a surface vessel, to map the head of the canyon. That system would collect about a 2-meter grid resolution data, and it's capable of getting out to, with resolution, to about 250 meters water depth, where its resolution essentially fades out. They showed, though, that there were beautiful concentric shaped bed forms. Some people call them now cyclic steps, that were on the canyon floor. And before that time, we didn't realize that they were there at all. Now, this was a time when MBARI was engaged in developing mapping tools to use to go to greater depths. And this is a picture of an AUV developed at MBARI. It carries a multi-beam sonar, a chirp profiler, and a side scan sonar system, and it's fully programmed to go down to the bottom, lock into the bottom, travel at 3 knots, 50 meters above it, and collect about 100 meter spaced swaths. These missions can last about 18 hours, which would cover about 8 square kilometers of the bottom. Now, our first developmental missions of this were focused on the upper canyon, where we would launch near the canyon head, descend down through the canyon system, turn around, come back down without coming to the surface, and then run back out at the bottom. And I might point out that that was a non-trivial thing to execute, because we have to navigate this without any GPS contact with the surface. So we're now doing this in a tight canyon floor. So we had to develop great confidence in the navigational abilities and the techniques to start doing this. But by by using an AUV in this, you no longer have to care what the water depth is in order to the resolution that you're going to obtain. And point out, when you're using an AUV at 50 meters from the bottom, even though it's the same sonar that you'd use from a surface ship, you have a constant level of resolution, and you can easily achieve 1 meter grid resolution of the bottom topography. And this is a little swath of data that actually shows some of these concentric shaped bed forms. It doesn't matter what water depth it's at. It doesn't affect the morphology. In this case, we're seeing that slope, a shaded relief map down below, which has contours on it. And the fidelity of these systems flowing in this way is now capable of contouring at about a 25 centimeter contour interval. Now, by about 2010, we had flown these AUVs in the canyon where all these red lines are, and had mapped out on the canyon floor to 2,200 meters water depth. And of course, very interested in seeing what the bed forms were like in this. And when we go down through the canyon floor, we see that these bed forms actually persist out to 2,200 meters water depth, which is still as far as we've mapped. I'd also like to point out, though, that when we map in canyons that do not head at the shoreline, we characteristically get a flat seafloor, a smooth seafloor. It lacks the textures of that are on Monterey Canyon. I also want to point out that the chirp data is perfectly distinct too. In side canyons like Soquel Canyon, we find that there's layered sediment. There are tens of meters of layered sediment might be there, but if you go on the floor of Monterey Canyon, we never find any internal reflectors in the sediment. There's actually no resolution that tells us anything about the internal structure of the near bottom sediments. Now, moving out now to 1,800 meters water depth, and this is a place I'm going to return to later in this talk. I'm first showing you the surface ship multi-beam survey that was data collected in 1998. And at this time, in this data, we had no idea that there were any bed forms in this area. There was anything of particular interest going on in the canyon floor. However, you overlay the AUV data, and you see that there are very prominent bed forms on the canyon floor that are there. The next slide is a perspective view of the same area, zooming in, and here we see the bed forms. This is a perspective view looking up the canyon, and I'd like to point out that the canyon floor to this depth is every bit as complicated and as much structure on it as a riverbed on land would have, clearly telling something about how material moves out there. And in the upper left, there's this contour map. Now, these are 1 meter contours, which is showing that some of these bed forms are having amplitudes that approach 5 meters. They're about 100 meters across. These are big features, just barely below what you could pick up with a surface ship a multi-beam. Now, I also point out that in ROV diving in this area, you occasionally find large boulders that are there. This is more than 1 meter across, granodiorite, but it's attesting to the ability of processes to move large things out onto the axial channel's floor. Now, monitoring. Now, the efforts that I'm going to talk about are restricted to the first 1,800 meters of the canyon, and that's where the coordinated canyon experiment was conducted. And this was an experiment that took place between 2015 and 2017, when 5 institutions put the maximum amount of equipment that we could muster into Monterey Canyon at the same time. And what we were doing is sharing the risks and sharing the benefits of conducting an experiment to try to learn about the processes that were passing through the canyon. And clearly this is the most extensive monitoring program we've conducted in a canyon at that time. Now, I would point out that Mbari, or my group, hosted the experiment. NOC, National Oceanographic Center at the time, was major participants. University Hall was major participants. USGS and Santa Cruz and Menlo Park participated, and Ocean University of China. And I actually see some of my colleagues on that this call. So hi, Pete. Now, what we were doing again was putting out this array of equipment that would extend with the moorings from 287 meters to 1849 meters in the canyon. That there were 7 of those that had downward looking ADCPs. They were suspended about 65 meters above the bottom, and the hope was that we would capture the sediment flows that passed underneath these instruments. There were also a number of other sensors in the bottom that were related experiments I'm not going to have time to talk about today, but I'd first like to just introduce the results from the mooring array. And I'm very pleased to say we captured 16 events during this 18-month period, which the frequencies of those initially took us somewhat by surprise. What's on this plot is, which goes from 0 to 2 kilometers water depth and covers the 18-month period of these deployments. That were 3 deployment events where we cycled the gear. We saw that there were 3 events that go down through the whole canyon system. There was 1 event that only appeared in 1 mooring in the middle of the canyon, but the rest of them were picked up in the first mooring. Some of those got to the second, some got to the 3rd or 4th mooring, but they dissipated someplace within the canyon system, ostensibly having started at the canyon head. Now, I'm going to talk about 3 of those, 2 of those events. Start off with the January 15th event, which was admittedly the most powerful event that we monitored. And what you're seeing here is ADCP data here, and it's plotted from looking down, going to the bottom, and it's on an arbitrary section of time running for 3 hours. And at the start of this blue area here, this white line is the seafloor. And at this time, we see that there was a dramatic change in this ADCP record. We see all this white section in here and the colored areas in here. Well, frankly, this is garbage data. It does tell us that there was onset of an event. It is garbage data because this entire mooring started moving down the canyon. It went 7.1 kilometers down the canyon. It did that at a speed of 4.5 meters per second. We know that because of the pressure sensors on the mooring before it broke loose and floated to the surface. Now, this flow then proceeded down to the next mooring, where it was captured 27 minutes later. It then moved this mooring a slight distance, 60 meters down the canyon. It moved on to the next mooring. That mooring moved a short distance down the canyon. And then this pattern continues down to the bottom of the array. And it did this as with an average velocity of 5.4 meters per second. Now, I'd like to point out one aspect of this, that for the discussion of what causes the flows or what's going on in the flows, important observation is that we essentially never get velocities that are actually measured with the ADCPs when the flows pass that are quite as high as the velocity that we calculate, the transit velocity from the arrival times of the flows at the mooring to the next mooring. And we know the distance, so we can get the velocities. And you can see that we systematically have higher transit velocities than we have velocities that we are able to record with the ADCPs. And that actually is telling us something about the fact that we're not measuring flow of water over the bottom, or not able to detect it with the ADCPs, which is as fast as the front itself is actually moving. Now, I just going to show one other piece of the ADCP data, and that's because this is the November 24th event. It's probably more characteristic of the flows that go on, in that we see it arrive at the first mooring, it goes to the second mooring. In this case, we see no evidence of it at the third mooring. It's completely gone. There's no turbulent cloud. There's no backscatter signal. We don't get, there's no record of that continued sort of dribbling down in a slow way in the bottom, to the bottom. It ended. I'd like to point out too that of the 12 events that had this characteristics, 6 of them actually had velocities that were above 2.8 meters per second, that at the time this experiment was done, what had been the highest instrumentally measured velocity. So these were more powerful flows than we had measured at the time. I guess the Congo work has since trumped this considerably. But so the most asked question about this experiment is what the triggering mechanism is. And let me dispense with this right now. There were no significant earthquakes during this time period. There were no river floods. In fact, this was an era of substantial droughts. There is a weak correlation with days of with high wave conditions. Now, Lewis Bailey has a paper that I think is in press now that's going to address this issue. Yes, the wave correlation exists, but is arguing that in fact that the propensity for these flow events is a cumulative result of how much sediment has been put into the canyon head by the longshore drift system. Now, as to monitoring, I've been talking about the time period from 2015 to 2017. And I now want to extend this to a time range which is going from 2002 and give a composite of all the records that have been in the canyon. So again, this is a plot that's going from 0 to 2 kilometers water depth. It's a very noisy plot, but anytime there's a little white horizontal line, there was an instrument that was in the canyon at that depth. So I've shown you the coordinated canyon experiment data here, which is just this 18-month time period. This composite, though, puts our observations into a bigger perspective. And there was, this is sort of anchored by work, particularly Jingping Zhu's work in 2002 to 2004. Bari had some gear in the Upper Canyon at this time as well. And I'd like to point out that if we look at the composite of these, and particularly a mooring that Jim Berry had in the canyon at 1,300 meters for most of this time period, we see that there are about the same number of events per unit time through this whole 20-year time period. And so we see a number of events that passed 1,300 meters. We didn't know where they went. In the CCE, we go somewhat deeper. We see 3 that passed them. At the time, we didn't know where they went and the like. But I think we can say a couple of things from this data. The coordinated canyon experiment was not an anomalous time. It is characteristic of what goes on in the canyon. And more than that, we do see a propensity for there to be more flow events in the winter than in the summer. And I think that comes through fairly clearly. Now, sampling. Now, this is a illustration of the number of samples that have been collected from the Monterey Bay area, mostly by Mbari. And I have to point out that there are 240 cores which we've taken in what's called the axial channel of Monterey Canyon. that starts to be enough to really characterize what the characteristics of this channel are. Now, we have collected these cores in transects, and we've been able to do that because we collect the cores using ROVs. And we've built our vibrocoring systems to put on the front of ROVs, which allow to go down to the bottom, collect the cores exactly where you want to collect them. And to give you an idea of ROV core collection, I'm going to have you watch a 5x speed up, but we're collecting a vibrocore. This is a 1.7 meter long core that has just been inserted. That's a vibrating motor, but it's also got a clamp on it, and it weighs about 50 kilogram object, which helps drive it into the bottom. So we've just extracted this core from the bottom. But one of the things that we can do is use a swing arm on the ROV to swap out core tubes in the system. So we're inserting this now full core tube in there. We're picking up an empty core tube. We're replacing it out. So we don't need to go back to the surface to get another sample. So we can collect, samples in transects quite productively. Now, given that number of cores, it's surprising that I have so little to say about the facies in a way, because the facies in the bottom of Monterey Canyon, if you're in the axial channel, are almost always just simple variants of what's shown on this screen. These are well-sorted sand, clean pebbles and cobbles, sometimes chaotic mixtures of mudstones, a lot of floating sand, clay clasts in the sand. And yes, you get a lot of variation within that general theme, but except for the clay cap on top, these are clearly density flow deposits, clearly deposited in events, laying down thick sequences quite quickly. Now, this is a plot of transects, a plot showing the areas where we have transects going across the canyon. And again, this is just a map of distance, and it's 400 meters across this whole illustration. And this is water depth going from 0 to 4 kilometers. And what I've outlined here are the areas where we have our most intense transects going across the canyon. And the areas that are in red are actually been picked based upon the multi-beam data, where we see the contrast between the relatively flat floor and the steeper canyon sides. Now, I'm pointing this out because it is surprising how fast the facies changes from being on the canyon floor and going up the flanks. And this is illustrated in this one place where it's narrow, one continuous thing, where 0 here for this profile mean we have 0 altitude above the thalweg. This is the 7 is next, and it goes up the canyon side. And very characteristically, you get a few meters off the thalweg, you lose the sort of distinctive thick, simple debris flow deposits. You can go into things where you get sort of thin bedded or thinner bedded turbidites. But if you're more than 20, 25 meters off the bottom, those facies have largely gone away. There may be siltier stuff in there, but for the sand, it's all down in this area, which I've outlined in red. In fact, the sand is all down in this someplace in this axial channel. Now, another thing that we have compiled is what is the thickness of the clay cap. And it turns out, if we look at the inventory of cores that we took from 2001 to 2015, vibrocores and push cores where we made these measurements, we know something about the clay cap thickness going down the thalweg. And this is a plot where we've taken the various bins of going down in 500 meter intervals, going down to the 4 kilometers, and look at the thickness of the clay cap with the numbers of samples that we've collected. And first of all, if we look out to 1,000 meters water depth, we get nominal thicknesses of clay cap. There is no significant accumulation of clay there. Not surprising, because the flows seem to be very frequent in that area. It gets a little more confusing, and there's a little bit more tendency to have a clay cap below 1,000 meters depth. There's a few here where we're getting up to 4 centimeters of material. It happens to be close to the Navy slump. But the thing I'd really like to point out is in this 2,500 to 2 kilometer bin, we see there's always a substantial clay cap thickness that overlies the first sand. And there's never been any sand exposed on the seafloor itself. But when we go further down the canyon, we see the clay cap thicknesses go back to something like 6-7 centimeters in it. It's fairly uniform. So we're seeing something different about this particular depth interval. Now, question comes up, has there been material transported to the fan in recent times? And I'm fond of efforts to look at DDT as a tracer of sediment transport. And this works in the Monterey Canyon pretty well, because the DDT, which was used extensively as a pesticide in 1945 to 1969, was heavily used in the Salinas and Pajaro Valley. This could be the type section for non-point source DDT use. Now, DDT itself, of course, may decay into DDE and DDD, but the sum of the three, which is the DDT residue, is what you actually measure, and that adheres to organic matter, and there's no known DDT use in the ocean. So if you see DDT in the sediments, it's been transported to the ocean with fine sediment essentially since 1945. So if we think about when the last major sand carrying event that passed, and in this case, it happens to be below 3,400 meters to match the C14 data that I'm showing the same slide, we characteristically see that there's DDT bearing sediment over DDT free sediment before we reach the first of these sand deposits. Now, so I point out the sand deposits are notoriously difficult to date inherently, because they really don't have forams. You can't rely on that, but they do have occasional pieces of wood in them in the line. And so that you can use just traditional C14 measurements of the wood. And I like to point out that if we start dating in the lower canyon, where in the wood from the sands, we see dates as young as 125 years. This was taken in 2005, which helps us constrain the age of it, because clearly that wood grew on land. It had to be transported to the ocean. It had to reach out 100 kilometers to sea, and ended up in the deposit. So in a way, this helps us constrain the timing of the last sand carrying event further out in the fan to being somewhere probably pre-DDT time, but younger than 1880, which incidentally would be consistent with San Francisco earthquake if you wanted to match it that way, but it's not a robust correlation. So the other comment I'd like to make about the sand, the total volume of sand that we have in Monterey Canyon, we know that there's at least 0.5 meter thick sand deposit that fills the canyon throughout this whole area, and we know its area. So we can actually calculate how long it would take to supply this amount of sand, given the current sand budget in there. And the answer to that is it's going to take more than 400 years to get this volume of sand in place. So it's a kind of getting trying to begin to balance the budget of the sand. Now, this is actually consistent with the work which has been done for OSL dating by Tom Stevens, that indicates that sand gets transported to 3.5 kilometer depths. This occurs on sort of semi-millennial scales. And the OSL dating also shows that the single sand grain spread increases as you go down the canyon, which indicates that there's mixing and temporary storage en route for the sand. So I'm now going to move on to repeat mapping, and I'm going to show 4 little places or zones where there's repeat mapping. In a way, I'm going to point out that there's massive remolding of the sand in the upper canyon. There's perhaps some deposition of sand going on 1,300 to 1,900 meters, and there seems to be no change in the repeat mapping we've done at 2,850 meters. Starting at the head of the canyon, this is a section that was mapped 6 times with the AUV during the coordinated canyon experiment. And this is a section of the canyon that's, about 15 kilometers of the thalweg, of the floor of Monterey Canyon. And what I'm going to show you here is a before January 15th mapping, November 4th, and after the January 15th mapping, January 18th, and talk about the difference maps. And you can't see much at this scale probably, so the next slide shows the same data for these 6 boxes. And if we look here, just blow up, again, you probably you have to study this for a while to see the changes by comparing the maps, but this is a before, after, and you can see big changes on the difference map. Point out this difference map scale is going from -3 to +3 color scale, and you see places in here which have changed, have gotten deeper by more than 3 meters off scale, and places which have gotten shallower by approximately 3 meters. So we're seeing these sort of very large changes in the canyon floor that are going on. Clearly, it's ripping up the bottom in a substantial way. I'd like to emphasize the fact that the bottom is getting ripped up by showing you what happened to instruments that were in the canyon at about 280 meters water depth in the January 15th event. I've already told you that we had an entire oceanographic mooring take off and go down through the canyon floor 7.1 kilometers before breaking loose and floating to the surface. We also had 2 other motion sensing indicators in the canyon floor. I'm not going to be talking about this. I don't have the time to talk about their science here, but one of these, this AMT frame, was anchored with a locomotive wheel that's 800 kilograms. It has feet that stick out 1.5 kilometers to sort of make it a tripod structure. It was kind of designed with the hope that it wouldn't move in the canyon floor. It took off and went 4.6 kilometers down through the canyon floor. And another item we'll call a bed, which is a benthic event detector. It's kind of a smart boulder. It's a whole separate talk about what actually happens internally within these flows. It took off and went 813 meters down the canyon floor. So clearly, we've got the capability of moving big things long ways in these flows. And the question is, how much sediment actually just simply goes beyond through this whole region. So if we look at the repeat mapping data from the canyon, and this is a composite of 6 maps that were collected in one section of the canyon floor. And for these 6 maps are doing there, you can see these bed forms here, and some of this data is not as good as others, but you can see the bed forms move up canyon. And this is a repeating illustration. You can see the changes here that as they move up from A to A prime, periodically you see the composite of this. This is the composite of the bathymetry that are put together for this time period. And the next slide would detrend this data. So this data now is detrended, and we're seeing, the 0 change is here. We clearly see some areas go up by, in places more than 2 meters, places down to the 2 meters. There's clearly an envelope in here where there is greater than 2 meters change in the bottom, and the entire section of the seafloor in here was completely eroded and redeposited during the time period of the coordinated canyon experiment. So I can say a couple of things about this from data firm. Now, the first one is, the question is there any net change that we see in the bathymetry during this time period? And honestly, that's looking for a small change in a big number. So we have no idea whether there was any net change during this experiment based upon the existing data. But we do know that the amount of remolding in the bottom of the canyon that's illustrated in this one section of it, which is only part of the canyon floor which is affected, had a volume of sediment that was remolded that would be equivalent to 6 years of the annual sediment supply. So we are massively moving, remolding this sediment. And ultimately, apparently, it's shuffling down the canyon in various stages, but it doesn't pick up and go out of the system. Now, the next area of repeat mapping is down at 1,300 to 1,900 meters. And again, we worked on this area during the coordinated canyon experiment, and a variety of things were done in this area. I'm going to be showing you the results first of the AUV mapping, where we mapped it 6 times during this time period. I will also show you the results of some more detailed mapping where we use an ROV with a multi-beam on the bottom of it to make, instead of a 1 meter grid resolution, 5 centimeter grid resolution maps at the bottom, which gets at the detail at a higher level. We also had other instruments down in here, which I will simply use as marker monuments. So during this experiment, the mapping it 6 times, we were able to again make difference maps of the canyon floor. And a difference map for this the area of the filament that's shown in the top is shown down at the bottom. And also, though, I'm going to come back to the 5 centimeter mapping, which has been conducted in this area, illustrated in the difference map of this star. Now, the thing I'd like to point out is when we've got below 1,300 meters, right below the Navy slump, and in several other bars down below, we see sort of convincing evidence of significant net deposition. And I'm going to go to this area right below the Navy slump and show that area again before, after, and this is for the entire CCE array. And I might point out that there's a conduit in here, which is passing through this constriction in the canyon, where the canyon narrows just down to 38 meters in width. And in this area, we see the development of a new bar. And this bar now has a color scale where it's showing that there's 6 meters of deposition in this area. This particular bar has a sediment volume in it, which is equivalent by itself is equivalent to 29% of the annual budget of sand that's entering Monterey Canyon. So, and this is of course just one small place. So we're starting to see evidence that sand is actually accumulating in this area. Now, moving to the big bed forms that I showed you earlier in the talk when using the AUV data. This is one section of it that's now been mapped, and it's been mapped at a 5 centimeter grid resolution. And it's, of course, you map a much smaller footprint. This is a 50 meter scale bar. It is showing the crests of 3 of these bed forms and the troughs of 2 of these bed forms. And so we mapped this area 4 times also. And because it was being done by ROV, which has a mapping sled on the bottom of it, which also incidentally has a LiDAR system on it, which is in development. Now, I'm not just to show you, just for an idea of the scale, for when you start mapping at this level, this is the instrument frame that photographed on the bottom. This is what it actually looks like in the 5 centimeter multi-beam data. you can actually start seeing the places where there are lines on the seafloor. These aren't artifacts. These are places where the ROV has landed on the seafloor and changed its texture. And this is, I point out the work that Monica Schweier hopefully will be finishing soon. I just like to look at some of the repeat mapping changes here also. And these SIN that I just showed you, the seafloor instrument node, it weighed about 1,100 kilograms. It got moved 26 meters during the January 15th event. And we were able to find it in the bottom and pull it out of the seafloor. In this map, we've already replaced the seafloor instrument node back on the crest of the bed form. And so since we now have actually 4 repeat mapping surveys, I'm going to show you just 2 of them from this area. And it's hard to display this data in all its detail, but I'd like to just point out that before, after, and a difference map, and the swipes across here in these boxes are what are shown to the right. So it's November, May, and a difference. And to reduce this even further, this blue line is a before, the black line is an after the January 15th, the red line is a difference. And this is illustrated here where we see, and it shows most clearly in the difference map where we see it's thickening here to something like 30 centimeters. It's perhaps diminishing a little on the crest of a ridge. It's thickening again, in this case, to about 60 centimeters, and then thinning and wobbling on it. And in detail, what's actually happening is we have filled in the hollows, we filled in the troughs some, and we've eroded the ridges a little bit. There's also slight indication that during the course of this experiment and this event, there's a net slight up canyon migration on these bed forms. But the primary change that we see here is deposition in the troughs that are of this area. Now, I'm moving out to 2,800 meters. This is an area where we have started surveys that are repeat mapping surveys at 5 and now actually 1 centimeter good resolution surveys are being conducted. We've selected areas where we think that there might be changes with time and the like. This is one scour feature. I like to point out that we've been mapping in this area actually since 2008 with clam beds to 2020. And we see that there's no evidence that any significant event had came through this area during this time period. So it doesn't look like any of the events that were captured in the CCE or, before most of the 21st century have actually gotten out to this depth. Now, I now move to repeat coring. And because of the CCE, we knew that there were things that happened extensively in the 2015 to 17 time period. The question becomes, how much further down the canyon did they go? And because of that, we immediately after the coordinated canyon experiment started a coring trip with the ROV where we cored both around the seafloor instrument node and out to 2,700 to 2,800 meters where we had cored before. And these are cores which were collected right around the SIN. These are cores which are collected in the area where we had the repeat surveys and the known difference maps. And these are all cores that we believe that there would have been net deposition during the time this experiment went on. And to me, frankly, when I look at these, there's no significant difference in these facies from what we see, for the sandy or the coarse deposits in much of the canyon. Perhaps these are a little bit more of the coarse grain facies than might get, but it's one relatively small area. And we actually happen to know in this case that this seafloor instrument node showed that the flow that is primarily responsible for the deposition of these events had a maximum velocity of 3.3 meters per second. So it's actually a context of what the velocity structure is and what it can do. So these are deposits that were laid down there. We also cored on 6 transects extending from this 2870 meter depth zone, or from the SIN at 1840 out to that. And on each of these, there are 6 cores in each one of these transects, only showing one of them. And again, these facies are all the same facies that we see elsewhere in the canyon system. There's nothing that was unusual about it. But the one thing that shows up from this is the thickness of the clay cap here. When we get to 2100 meters, it again dives in thickness down to, you know, something up to 40 centimeters of clay cap was there, and you know, presumably that it's there because it, you know, it has persisted. And to point this out, there's really no difference from the pre-CCE data, you know, further down canyon. There's a little bit of wobbling here, and this probably has more to do with exactly where we collected the surveys. But at 1900 meters, there was no significant clay cap during this these visits. However, 2100 meters, and that there was no 2000 to 21, but 2100 to 2500, the clay cap that's there has persisted. And it appears, of course, that the thickness of this suggests that these events didn't get there. And perhaps the reason that there's a thicker clay cap there is this is where turbid clouds have been dumped in the recent past. Moving to 2870 meters water depth. And again, this is where we cored in 2017 and 2014, you know, repeating what we did in 2014. And within a few meters, these cores are from the same sites. Lithologically, they're essentially indistinguishable in there. So, you know, we see no evidence that anything had changed. Of course, the clay cap is about the same thickness. And I'm showing this core because lead-210 was measured on this core in 2014. It was repeated in 2017. This plot here is actually showing it not on a log plot, it's a concentration plot. The log plot produces large errors for the timing of it, so it hasn't been terrific for the chronology, but it clearly shows that there is increasing depletion in lead-210 with depth, and that this is a profile for both of these that are the same. There's no indication that this clay cap was ripped up or that anything has gotten to this depth during this time period, and which would correspond with the CCE. So sort of finally, and beginning to sort of conclude is, I think that there's been no recent flow events in Monterey Canyon which have penetrated below 2100 meters water depth, which kind of puts in perspective what we did during the coordinated canyon experiment. I also, being interested in repeat mapping, I also want to consider what the annual sediment budget of Monterey Canyon means for our ability to repeat map. And I, you know, knowing again that we know the area, we know the volume of sand that's in here, it would, if we deposited the sand uniformly over the given area, this would correspond to just a 6 centimeter net increase of uniform distribution. Of course, is not the case during the CCE, which is actually way below what we can detect with AUV surveys over relatively short periods of time. But I point out that if we then expanded this for a 20-year time period, more or less, we would get 77 centimeters of deposition in this area, which starts to get into the realm that you might be able to start tracking it ultimately with repeat mapping on multi-decadal time series or even decadal. And now just as a sort of a summary of this, the mass balance of things, which I think is a source to sink concept. Well, we know that the sediment transport events in Monterey Canyon are occurring on a subannual basis, and the no flows that penetrated below 2,100 meters in probably the last 20 years. The last output to the fan is ballpark 100 years ago in there, which means that the present inputs and present outputs are not balanced. So we're definitely accumulating sand in here. And I think that it's primarily between 1,300 meters and 2,100 meters. And to me, looking at these data, say, there's a mental paradigm shift where my old concept of the canyon was a conduit for sediment transport. And thinking on the longer term records, I'm going to flip that and think about the canyon as a capacitor for sand that will ultimately be discharged on the fan either by staging or in individual large events. So I think I'm probably running out of time here, but I just point out that we do know that there are thick sand deposits that fill the canyon out to 3,900 at least. We know that these are remolded in the upper canyon extensively, and we can document that out to 1,800 meters, but none of it has gotten beyond 2,100 meters based upon this collage of information. And I think that the flow that we're seeing in the 21st century are simply staging events for processes that are of a larger scale. So thank you.
Oh, Charlie, this is a fantastic talk. And so I know some of have to rush away for a 10 o'clock class. If you do have a question, please go ahead to ask. But I want to say this, in February, we have a whole bunch of talk is lined up. Like next week, Donna will talk about the modeling work. Tom Bianchi talk about the Delta front estuary, the carbon stuff. And we have a Nile River, we have a Daniel River, Neil Blair, February 19, we'll also give a talk and also a couple more talks. So mark your calendar. So now, if you have any question, if you have to rush to leave, you want to ask, go ahead to ask. If you can wait a little bit, you can, wait a little bit. Go ahead.
I have to pick up my son, so I'm going to run off in a moment. But
go ahead.
I was interested in the long run out events, Charlie, you had, and you said that they keep getting down to that deeper level, but actually 2 years you didn't have any. And so it looks kind of episodic, not really kind of regular. And I know Pete has written about bed thicknesses being kind of like Paull law distributed. And I wondered if there's more to it. Probably statistically, it's not very well characterizable.
Well, so in that regard, I think you're referring to a slide
earlier on, yes.
Got to get back. I may have to go out of display mode to get back.
Yeah.
So I think the answer to that, oops, I went by too fast. So some of the ones we didn't have any, but you notice we didn't have any event, we didn't have any gear in the canyon during the winter.
Oh, okay.
So that hole in there, and maybe I didn't point out well enough that the events characteristically occur in the winter.
Okay.
Charlie, you want to reshare your screen if you want to?
Oh, sorry.
Yeah, because I stop your sharing.
So I'm in the PowerPoint thing. I'm not sure I know how to get back to, I'm on, do I have to end the show? Let me see where I can get to something to reshare.
Share screen, yeah.
Share screen.
I'm seeing my prepresentation. It dominates everything on.
Oh, you can use the escape button on your keyboard.
I guess I got to escape the PowerPoint.
Yeah.
Share screen.
Should be on the bottom of the Zoom.
Oh, yeah. Who's next? Go ahead.
Yeah, that one. Okay, so you've not got
Yeah,
Not
so
got the winter.
those winters are missing.
Oh, sorry, I missed that. Yeah.
So it's not a continuous record, but it's most of the time that Jim Barry had a record out there.
Yeah. It would be hard to characterize the episodicity in that, I think, with the missing records.
Yeah, but the general pattern. I mean, I don't know.
Yeah.
If I see, there's nothing really different from the, from if you look at these things in composite and think about it as one instrument, one place. It's hard to make a case that the Coordinated Canyon experiment was an exceptional time period and that the 2002 period was exceptional either.
Okay, great. Who's next? Hey, Charlie, I have a question. You mentioned about the move of the SIN, SIN, of 26 meters. So is that moving is only the pure instrument was pushing down, or the whole block of the sediment body was like a landslide going down?
Well, I think that question is very open as to what's going on in the upper canyon, as to whether it's the whole block of sediment. In the case of the movement of the SIN, which is down at the bottom of this array, I think it slid over the bottom, and that it was probably moving with other material that moved apart from the crest that got deposited in the trough. Okay. And because the purpose of that SIN is ultimately was to catch the passage of flows going over the top, over it and looking up from the bottom. And there were 3 frequencies of ADCPs in there. And this is work which ostensibly is being championed by University of Hull. Steve Simmons and Dan Parsons are doing this. I think that I don't know. I'm jumping to a conclusion that they haven't enunciated, but it looks like that flow was actually collapsing at the time that it passed that area. So.
Okay, cool. Liz, you want to speak your question?
Sure. I'm more of a long-term time person, and so I was looking at that event that you said was maybe the earthquake, and thinking about land use changes. So. Do you think maybe the role of the canyon might have changed with, sort of all that farming that's going on now or across the last 100 years or so?
Well, I wrote a paper about the sediments in the upper Monterey Canyon, and it's I think it's got a title of something about discordant C14 stratigraphies. That was looking at the invasion of bomb carbon into the canyon and the invasion of DDT into the canyon head. And in that paper, I argue that the patterns that we see in the canyon using the what we know about the chronology above and below the DDT and the bomb carbon horizon indicate that the sedimentation rate in the previous time periods was much higher, and it's anchored at the bottom by disturbance pollen. And so my argument there was that there was a much higher sedimentation rate during the early 20th century, late 19th century, early 20th century period, where there was terrible land use. And in fact, if anything, we've gone to a thing where it's now relatively sediment starved. So this time period is probably has less sediment supply than a century earlier. And we have no idea what it was like before humans started screwing it up.
Yeah, thank you. That's a great perspective. And I also wanted to say, I love that you're the combination of tracers that you're using, including the organics. That's just, I found that very fascinating. Thank you so much. It was a great talk.
Thank you. Okay,
great. Charlie, here the question in the chat room. Wang Xixin from Qingdao, he said, Charlie, it is a very nice talk. Have you considered the sand from tributary canyons?
Well, we in a little bit, yes, because when I give this sediment input from the head of Monterey Canyon, it is leaving out Carmel Canyon, and Carmel Canyon does produce a noticeable addition to that, and it would be adding to the section which I'm highlighting. That's at between in the vicinity of 1900 meters where it merges with Monterey Canyon. It'll be putting more sand in there, but there's no evidence that the section that nothing is passed out has had a contribution from Carmel. So when we get out into the fan and say that it takes at least 400 years to produce that amount of stuff, that is the input just from Monterey.
Okay.
And honestly, we don't know the input from Carmel as well, but it's a modest percentage of it.
Okay, that's fair. So I saw Dave Dumas also unmuted. Dave, do you have a question? If you have a question, go ahead. Then next is Peter. Okay.
Okay, yeah, I had two kind of chronology questions in the optical stimulated luminescence data. What do you envision as the time zero when the quartz was exposed to light? Is that back on land? Is that when the sand is on the beach or on the shore face, or what's time zero for OSL?
Yeah, it did a fundamental question to this, and didn't go into this, but we collected sand from the beach. We cored extensively at 100 meters, and the sand on the beach was essentially zero. At 100 meters, it gave us a composite age of about 10 years, very low age. And then there were 3 other places down through the canyon and stuff, and we saw a progression of ages as it went down the canyon.
Okay, yeah, perfect. So it is kind of beach age when it was last on the beach.
And we also in those samples were able to date some of the finer sediments on the canyon side when you start to getting up with the turbidites mixing with the hemipelagics. And in that case, we find with OSL dating that the 4am ages that you can get on the side of there are much younger than the OSL dates of the sand. So you can date above and below a sand and do an OSL date on it. And that's another way to get it at the spread of time. That sand has taken some time to get there. In terms of the things though, for Monterey Canyon and the fan, I didn't really go into this, I didn't have time. When we go a short distance up the side and date these beautifully layered turbidites that are there, we're usually not dating the thing which is the last event, and we know that because of the wood. So the last event actually wasn't the ones that was laying down the sand that might be 25 meters up from the thaw whack, which is a complication you need to think about. That there's a big assumption in some of the turbidite dating that you're actually you're actually sampling the last sand.
Mm-hmm. One other quick comment is that for the lead-210 and muddy cap, you reported, it looked like anyway, you reported in DPM per gram. You might consider doing it DPM per gram of fines just to make sure there isn't a dilution effect with coarser material, because the lead-210 will be on the silt and clay size material. Sure. And as you build in sand, you could get a dilution that would cause DPM per gram total to decrease. That might not be DPM per gram fine decrease.
So good point. And I think Nora Naminsky, who's sort of working that stuff up, is trying to chase some of those vagaries now. So,
okay. Okay.
Great. Wonderful talk. Thank you.
Thank you.
Peter, go ahead.
Hi, Charlie. Hope you're doing okay. It's good to see you. The thing that seems to kind of stalk all the way through it are budgets. So listening to everybody on source to sink and people thinking in terms of budgets, it seems that here you have like 2 parts to that. Sometimes you have a little bit of sediment coming in the top and it's like a rock in a carpet. You get lots of movement through the carpet, but not much stuff coming out the other end. And then the other thing is just that the events that discharge the capacitor, the multi-100-year events, and or whether they're earthquake triggered, that's the thing that needs to be understood for the final steps of the picture. Do you think any of the dating techniques that we have individual fractions of organic carbon, the more sophisticated newer end dating techniques could help us with those infrequent events, because it's not going to be monitoring probably. It'll be some sort of geological dating exercise. Do you see any way of going after the big events?
I think that'd be a great idea to go after that. Honestly, we were working in the Lower Canyon early in the time we were working on Monterey Canyon, and then for a variety of reasons to switch back up to the Upper Canyon. And unfortunately, the density of measurements of one type from the top of the canyon and the bottom aren't time synchronous. So, but I think it'd be a great idea. You know, these cores all exist if you're looking at proxies that are going to survive. You know, in a core archive, we've donated all our cores to the USGS's archives. I'd be glad to work with you on that too. I mean, it's
that's good. Okay. Is Dan Tack from Leeds still there? Dan, are you still there? If please,
yeah,
go ahead.
Yeah, I'm here. Hi, Charlie. Thank you very much for an amazing talk. I was really interested by the data you showed from just downstream of the Navy slump. I was wondering if you saw any sort of signature of things happening upstream of it as well, or whether you have any data on that. Any like ponding or anything happening up there?
Well, no, and I probably neglected to say that the slope from 200 meters to 1250 in Monterey Canyon in the stuff is essentially linear. It has a slope of 1.8 degrees. It really, you know, it's a line rather than a normal river profile. So I take that to suggest that the stuff that was in the area that we did map during the coordinated canyon experiment, which really only went to about 600 meters with the mapping, is probably characteristic of what gets out to about 1200 meters. And I say that also because the events which were moving stuff through the whole system, you know, enough of them happened during that time period so they know they passed through there. So, you know, partly, I think that the 1300 meter Navy slump thing is really a change in the behavior of what's going on in Monterey Canyon right now. So that section out to 1300 meters, I think is probably net acting as a simple capacitor. I mean, not a capacitor, a conduit. And below that, we get into the place where we're accumulating. But can I fully justify that? No, but that's my best guess.
Okay.
Nice, thanks.
Great. So Charlie, I have a question. You know, in terms of the canyon study, Monterey Canyon maybe represent the most extensive, comprehensive study all over the world. So in your opinion, I want to hear, compare Monterey Canyon, Congo Canyon, or Goping Canyon in Taiwan, even the canyon in the Bay of Bengal. What's the common thing we learn, or what's the unique thing of the Monterey Canyon? That's a big question, but can you try to briefly cover this part?
Well, I think the thing about Monterey Canyon is it's connected to the shoreline. And as an end member, it's a shoreline connected canyon system. Now we see crescent shaped bed form type sand movements in, I think it's the 9 canyons that we've mapped along the California coast that are connected to the shoreline. We see that bed form pattern in all of them. We haven't mapped in as many canyons that are not. I think that we've mapped in 4 canyon systems that are not connected to the shoreline, and they do not have the crescent shaped bed forms. They do not have these characteristics. And I might point out too that the canyons which have crescent shaped bed forms in them and then are of this type are all associated with the same types of sand deposits along the California coast. Most of them we know contain modern carbon where the crescent shaped bed forms are. And I think we're just looking at one type of conveyor belt that's moving the material into the deep sea. And that type of movement is probably not going to go on in quite the same thing is not going to go on in other canyon systems.
Oh, so you mentioned the carbon. And anybody estimate how much terrestrial carbon, organic carbon transport the canyon? You know, you talk about sand budget. Anybody talk about the carbon budget?
Yes. Now, so my colleague Jim Barry, that's the main reason he's had that current meter in the canyon during the time period, is he wanted to be looking at carbon transport through that area. You know, he wasn't focused on sand, he was on carbon. And I am quoting, I'm trying to, the numbers is unclear to me, but he also had sediment traps and moorings. He had sediment trap there and moorings during all those deployments in a control site that's the same depth that was outside the canyon. And there were orders of magnitude more organic matter moving through the canyon than were accumulating at the same depth on Smooth Ridge. And the punchline of his talk is, to the first approximation, the canyon is the main conduit for movement in Monterey Bay, and perhaps the only thing that's significant. The amount, the hemipelagic rain is trivial in comparison with what moves through the canyon. He's also tracking, though, the ambient movements in the canyon. The canyon floor is characteristically quite turbid, and in organic carbon, the story is not just in the sediment transport events that I'm talking about. The organic carbon thing is, you know, every day is important in Monterey Canyon.
Very good. Okay, that's fantastic. Anybody else have any question? Okay, if not, once again, this talk is also live streaming and archived on the YouTube channel. And so you can go ahead, you rewatch this talk. And thank you, Charlie, very much. I know thank you for your earlier morning, all the way from 5:30 a.m. until now. So thank you very much. And you welcome coming to next week or until May. Every week we have 2 talks a week. So enjoy this pandemic locking down home time. Okay, thank you. Bye-bye.
Thank you all.
Thanks, Charlie.